Okay, today we're starting Unit 3. So for those of you who are at home listening to this lecture, it is going to be correlated to the Unit 3 blank notes. So get those out. Everyone else, let's do this. Now, the one thing I want to talk about when it comes to these AP equations and writing AP equations is that this is very specific to the AP exam. This is not going to be in a textbook. Unfortunately, it's something you're just going to have to learn and fight through. It's not easy. You're going to spend a lot of your time struggling to get the consistency of it. It'll probably take you most of the year in all our practice that we're going to be doing for you to really understand it. So I'm telling you this not to discourage you, but to just have you chill out. Breck. Hey. I'm calling Breck out. Anyway, so AP equations are always number 4 on the AP exam. It's the first question of the free response section. Okay? It's worth 15 points. That 15 points is worth 15% of the free response grade, which is 50% of the exam. Not going to do the math, but what's good about these AP equations is I know they're coming. I'll get you prepared for them, and it's something that could be the difference between a 4 or a 5 on the test. So I'm teaching to the test on this. So the most important thing is to know your solubility rules. Now I know there was a lot of confusion about the hydroxides. There's some clarification here, but you have to realize that a few of these are in such a gray area. For instance, the calcium hydroxide, that actually can be written either way. If it's super, super concentrated, it's insoluble. If it's like 0.1 molar, it's soluble. So the AP readers will accept either soluble or insoluble for those. So don't freak out about them. As we do problems, I'll address the different solubility issues, and you can take note of that. Okay? So moving on. Points. Each reaction is worth a total of 5 points, and on the AP there are three reactions. Okay? So we usually give 1 point for reactants, 2 points for products, 1 point for balancing. You've got to balance every equation in electrons and in number of atoms. And then there's always a question. They might be oxidation numbers. They might be is it soluble or insoluble type questions. They might be what color would this turn litmus. Real descriptive chemistry type questions that are found at the end, and that's worth 1 point. So a total of 5 points per question, and that would be 15 total for 3 questions. Okay. The best way is to practice, 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 practice. You have to do all the homework that I assign you. You have to do everything. So we'll talk about where you get the homework for this at the end of the lecture. Writing AP equations. AP equations are found in the free response. I already talked about that. 3 equations must be balanced, followed by a question, and we'll talk about scoring when we do some extra credit grading on this in the future. So let's start filling in some notes here. Things you need to know when doing AP equations. The first is know your solubility rules. Know your solubility rules. Solubility rules. But you all know them already, right? Absolutely. Say that louder, Ms. Richard. Of course. Okay, so now everybody knows. All right, number 2. These are net ionics. What does that mean? We have no whats. You cannot get credit if you have spectators in here. Okay? If you get 1 point, if you only get 1 point for reactants and you leave a spectator on the reactant side, you get nothing for the reactant point. Okay? So you have to get rid of all your spectators. The good news is, though, that all the reactions happen. There are no reactions. So you never have to look at an activity series and say, oh, is this single replacement going to happen? They all do. And it says it in the instructions on the AP exam itself. All right, the next thing that's important is the need to balance all your equations. Very important. Do not include states of matter. The reason I'm telling you this is because if you get them wrong, they'll affect you and you could get points taken off, and they're not required, so why do them? Right? Because if you make a mistake with them, it could cost you. By that I mean, y'all know what I'm talking about, AQ, S, etc. All right, number 6, try and make double replacement over redox first. I know that doesn't make sense right now, just write it down, and when we get to double replacement tomorrow, not tomorrow because it's late arrival day, the day after, I'll address that. Try to make double replacement happen first. What happens is I'm going to teach these to you type by type by type. I'm doing the hardest one first, which is redox. But then they start getting mixed up, and you're going to look at one, and you're going to be like, God, is that anhydrous? Is it decomposition? Oh, wait, is that double replacement? No, it might be redox. So there's a lot of confusion. If you follow this and always try to make double replacement happen first, it's going to help out a lot. It's a little trick of the trade. Okay, moving on to a little review here. What are our strong binary acids? Correct. HCl, HBr, and HI. I bring clay. Okay. What are our strong ternary? What's the rule of thumb? 2 or more O's than H's. Y'all remember that from like 2 days ago? Yeah? Okay. And then what's always weak? Carbon containing acids are always weak. Weak. That's so weird how they're seeing this. They're gonna see the writing come up as I'm talking. All right, that is creepy. Let's talk about our hydroxide. What are strong? Group 1 hydroxides, and what 2? Ba and Sr also. Everything else is weak. Okay. It's really messy writing. Sorry, folks at home. Okay, moving on. Let's go to our first type. Our first type are the redox reactions. The original packet that I have here, written by other people, and I've adapted it and changed it, had probably a set of 50 rules that you needed to memorize, which made these so much harder than they need to be. A lot of this stuff is an intuitive thing that you'll get. The rules on number 1 that you need to memorize when you're working with redox equations, you'll find them on the next slide right there, okay? It's actually not on the next slide. Y'all have it all on one page in your notes. But those are it, and we're going to kind of memorize them as we go through. On tomorrow's quiz, I'll provide these for you. Only tomorrow. Provided on first quiz only. Once you see them in use, they won't be so scary, so don't freak out about it. But I'm going to go back now, and we're going to fill some of these in. So memorize some rules. I'm referring to those that I just showed you. It's important that you know your divalent charges. I'm not going to go through those right now, but what I mean by divalent charges, no divalent metal charges. What am I talking about there? Metals that have more than one charge. So give me an example of one. Iron 2 or iron 3, copper 1 or copper 2. All those we went over the first week in class. Okay? Example, Cu plus 1, and so on. The reason is you need to know when metals go up and down in charge, what they could go up to or down to. And the only way you'll know that is if you know those charges by heart. Okay? Again, this might not make sense now, but it will, I promise. Polyatomics will decompose to gases when they can. Polyatomics will decompose to gases when they can. And again, hang on to that. It'll make sense shortly. Number 4, what does it mean to be redox? Something goes up in charge and something goes down in charge. It can't be redox if that doesn't happen. So that's going to be your go-to rule. Okay, number 5 is a controversial rule, but it works. Go to metals first. Again, you'll get it in a minute. Go to metals first. And number 6 is kind of a combo rule. Never write down group 1 ions. Why wouldn't we write down a group 1 ion? Because it's a spectator good. Now the only group 1, and then I'm going to say ion here. There's going to be cases where it says sodium chloride solid is added. If they say that in the problem, you're putting in NaCl solid, so you would include it. It's only when they're saying a solution that you have ions. So I'm going to write here unless in solid form. Another thing I don't want you to write down is a nitrate. Nitrate's not included unless adding, I'm going to go up to the side to be funny, nitric acid to a metal. If you're adding nitric acid to a metal, the nitrate is actually part of the reaction. Otherwise, nitrate's going to be a spectator. So, nitrate is not included unless you're adding nitric acid to a metal. Okay? Any questions on those rules? I know they kind of don't make sense yet, but we're going to practice. Y'all ready to actually do these? So those are the rules, and then here we go. A solution of tin 2 chloride is added to acidified solution of potassium permanganate. Your job is to write the reactants and predict the products and balance it and the whole jazz. Okay, whole 9 yards. So when I start this, I don't want you to freak out. What I want you to do is read what it says. A solution of tin 2 chloride. What does that mean? Aqueous, and it's dissolved. So we're not going to worry about it. We're just going to write tin 2 chloride already split up. So we're going to write SN plus 2 plus Cl minus. Don't worry about balancing it or any of that. You will do that after. What we're doing is we're doing this the shortcut way. You're not doing molecular, total ionic, net ionic. We're doing it like this right off the cuff. Okay? Is added. What does it mean to be acidified? Has H plus in it. So there you go. I'm going to put H plus in it. So when you see the word acidified, we're going to add H plus. To a solution of potassium permanganate. What does solution mean? Ions. But what's that first ion? Potassium. It's a group 1, so I'm not even going to write it down. I'm just going to write down the permanganate. Now, the reason I know that this is a redox is because I see that permanganate in an acidified solution. And I, because of my experience, know that's a rule. So look at your rules. What does a permanganate in an acidic solution produce? Mn plus 2. Look at your rules. Mn plus 2. So that takes care of half my work. So what I have to do, remembering that something goes up in charge and down in charge, what did the manganese start at? What was the charge of this manganese? Plus 7, and it went to a plus 2. So that went down in charge, right? So now I have to make something go up in charge. This is where the rule, go to metals first. Go to the metal first and see if you can make it do the other thing. Sometimes you go up in charge and need to go down. It depends. Here, we went down in charge. Now we need to make it go up. Can we make the metal go up? Yes, you have to know. That's why you have to know your charges. What are the possible charges of tin? 2 and 4, so that's plus 4. So that went up. We made something go down, something go up. Did we need the chloride ion to make that happen? Did it play a part? Nope. Bye-bye, chloride. Okay? And now the last thing is, what are we missing to make this a balanced equation? We're missing oxygens. Think back to balancing redox. We had H plus on one side and water. You're allowed, guys, just to throw water on the end. That's it. If we were just to add H plus on the other end, that wouldn't help us get O's. All right? So here's the thing. On your homework for redox, because I'm going to have you practice bazillions of these, I'm not going to make you balance the tough redox ones like this. Because at this point now, you would have to balance this using the half reaction method. So you'd have to pull out your M's. We just don't have time for that. On the test, you'll have to, but you only have 20 questions on the test. I'm okay with that. So for this, I'm just going to give you the coefficients right now, but write yourself a note. You have to balance with the half reaction method. And I'm not practicing the, you know how I said there's always a little question afterward? You guys are just going to have to study that on your own. And practice that when we do quizzes. I can't prepare you to answer a question about things. Balance with half reaction. All right, so the coefficients in this were really a 5 here, a 16 here, a 2, a 2, a 5, and an 8. So after balancing, that's what you would get. We don't need to have take time, class time to do that, okay? All right, next up. Any questions before I go on? Okay, a solution of tin 2 sulfate. What do I write? Sm plus 2 plus SO4 minus 2, right, is added to a solution of iron 3 sulfate. And it's a solution, so I can write that. Okay, we need to make redox happen. I don't see a rule here or anything. So I'm going to see, can I make something go up in charge and go down in charge with the rule go to metals first? What are my options? Can iron go up anymore? It has to go down. Go down to the 0, and I'll tell you why in a minute, instead of the plus 2. Go down to the 0. And what will tin do then? Up to 4. And the reason we had to take tin up is because iron can't go up anymore. I know tin can go down, but it didn't work in that case. So now we didn't need the sulfates. Those are spectators, okay? So this can kind of be by inspection. I see there's a difference of a factor of 2 for the tin and a factor of 3 for the iron in terms of charge. So I can say, hey, I have a 6 factor in my charges. So to balance this, and again, you can do half reaction method. I'm just going to give you the, so that gives 3, that gives 12, that gives 6, and 6. So I've got a charge of 12 on both sides. So you always have to balance charge and atoms or ions. They have to be balanced. Okay. Y to 0. Do y'all remember the saying? I hope I have room for this. As Stan fell, what happened? Exactly. Huge cups cracked. Other than cracked, because chromium actually can have more than just 2. Arsenic, tin, iron, and mercury, all of those can have multiple charges. If it's in this saying, the higher charge is common. That means these don't like the lower charge. They would rather be in solid form than in the lower charge form, okay? So in this case, iron 3 doesn't want to go to 2 because it's not the most common ion. So instead it's going to go to 0. Now I really don't want to say this, but on the AP they actually will give you credit for 2, even though that's not what happens. I prefer you to actually know what happens, okay? But at the end of the day, they're going to give you credit. Go ahead.
So Bob, would you only give us credit if we wrote 0 as opposed to plus 2?
Yes, that's the plan. Now, if everyone's tanking it, I might be nice. But I'd prefer you actually, let's play that one by ear. Let's try to do it the right way, okay? All right. This one is kind of iffy. Hydrogen peroxide. Any questions before I go on? I keep forgetting to ask. All right. Looks like we're still recording. Okay. Hydrogen peroxide, what do I write? H2O2. Is added to a solution of iron 3 sulfate. Solution. What's wrong? No, hydrogen peroxide is a covalent compound, right? So do covalent compounds break up into ions? No. Thank you for bringing that up, though. Okay, so looking at this, here's the thing about hydrogen peroxide that makes it really special, is that this O has a -1 oxidation state. Not a good place for it to be, okay? Hydrogen peroxide can both be reduced and oxidized. Which way do we go? Do we make oxygen, which takes us to 0, which would be up, or do we make water, which would take our O to a -2, which would be down? Which way do we go? Which way? Well, you have to determine it based on that. Go to metals first. That metal can only go one way, which is what? That metal can go up? What? Down to where? 0. Okay? Because that went down, whatever we get from the component, what? Okay, either, oh, it is? Oh, hell's bells. Okay. All right, I didn't say hell on recording. Okay, so I got to revamp our thinking here. All right, because iron can go either way, the question is, which way do we go with the hydrogen peroxide. Here's the DEMO rule. DEMO rule, make water first. Think about all the people that have dirty water. We want to make water first. DEMO says, I'm going to have to put the dots there. DEMO says make water first. So go ahead and make the water first. And then in making the water first, what happened to that oxygen? It went down to -2. So now then we have to make the iron go up. So that's what makes this one tricky, is remembering with hydrogen peroxide, make water first. But the good news is anytime you see hydrogen peroxide, that's a clue that it's going to be a redox equation, because that O-1 is super, super unstable. Okay? What, are you okay, Angela? You got it? Okay. Yes, Abby. Yes, I'm not done quite yet. I was going to talk about balancing. So did we need the sulfate to get there? Nope. And so when you balance this, you're going to pull out your water, and then you're going to pull out your water and your hydrogen peroxide and balance, pulling out your water. In doing so, you're going to end up with H plus over here. Not because you put it in originally, but you know when you balance, sometimes you have to add water to one side. It's going to come out in the balancing. Okay? That's something you will see when you actually do the balancing. 2 and 2. And that's a balanced version. All right, next one, you'll get this one easy. This one won't be quite as difficult, even though it looks scary. Potassium permanganate solution. What do I write? Just permanganate ion. Good. Is added to a solution. Here's where knowing what we did with net ionics last unit is important. It's a solution of oxalic acid. What did we do with solutions of weak acids? Keep them together. So oxalic is H2C2O4, right? And it's acidified with a few drops of sulfuric acid. What do you think is important about those drops? What are they putting in there that's crucial? H+. We don't care about the whole sulfate thing, okay? When you say acidified with anything, it's because we're wanting to add H+. We need that because permanganate won't do what it's got to do unless it's in an acidified solution. And this is too weak to provide enough H pluses to make it happen, so we got to add a little extra acid. Now, what does permanganate make in an acidified solution? Mn+2. So you probably already know that one rule just from practicing, right? Where am I? Okay. Now, here's the thing. What happened to that charge? That went from +7 to +2. So we have to make something go up in charge. Do you see another metal we can go to? No. So now I'm going to talk about that other rule that I said really didn't make much sense yet, and that was when given the opportunity, polyatomics will decompose to make gases. This is a polyatomic now that's going to be dealt with. The gas we make, it's a gas you know. We always make stuff you know. So don't try to create some crazy gas no one's ever seen. Just think, what? I heard it. CO2. Let's see. Will CO2 do what it needs to do? Again, we made permanganate go down, so now we got to make something go up. Looking at the carbon, what's the carbon? I'm just going to take oxalate by itself and let you give me the charge of that carbon. -2 times 4 is -8. To get an overall -2, this whole thing has to be 6, but there's 2 of them, so each one of those is +3. What happened? It went from a +3 to a, did that go up in charge? Yeah, it did. That's why carbon monoxide wouldn't have worked, because that would have then taken us down as well. We had to go up because the permanganate or the manganese already went down. Okay? So what do I need to tack on the right to make this thing balanceable? Water. And then you're going to do your half reaction balancing, and then when you're all said and done, you're going to get a 2 there, a 5 there, a 6 there, a 2 there, a 10 there, and an 8 there. Y'all comfortable with having to balance that using the redox method? Okay, any questions on that one? I'm just giving you every type of scenario you might see. Okay, when you do homework, you're going to do multiple where you have to do the polyatomic thing, multiple you have to do the metal thing. I can only do 1 or 2 of each, okay, in class. All right, next slide. For me, not for you. A piece of iron is added. Oh, I love this one. What does a piece mean? Solid. So what does that mean? No charge. Is added to a solution of iron 3 sulfate. I'm not even going to write the sulfate down because looking at that, go to metals first. I can make redox happen. What can I make? I'm going to do it in one step. But Fe plus 2. That's it. You see why that takes care of everything? Okay, and to balance this, I have a common factor of a charge of 6, so I need to have a charge of 6. So to get a charge of 6, I put a 2 there, and I put a 3 there. That's 6 and 6. Oh, 3 irons? 3 irons. How nice. The ones that are easy like that, you're gonna like them a lot. Right, because some students are saying, how come you don't take Fe0 to plus 3 and Fe plus 3 to 0? What would that be? No reaction, right? Because everything would cancel. Do no reactions happen? Mm-mm. Make sense? How you doing, Joe? Can you see? I know I'm kind of like right in your way. If you can't see, it might be good to move. Okay, solid sodium dichromate. What do we write? It's solid. This is where you include the group 1, okay, in a scenario like this. Na2Cr2O7 is added to acidified sodium iodide. It's a solution of sodium iodide, so what do we write? No Na. It's a group 1, just the I minus. See, it's okay to write the Na down, but you're just wasting your time. That's why I'm trying to make this a shortcut. I smell a rule here. Dichromate, permanganate, big indicators of redox. Is there a rule about dichromate in acidified solution? Cr plus 3, okay? Now, looking at this, now you can't, people say, oh, the sodium can change charge. You can't have redox occur within the same compound, okay? So we had chromium going from what charge to what charge? 14, negative 2, that would make it 6. That's a plus 3 again. Going to a, oh no, it can't be. What am I doing wrong? I have to do it because I can't do math in my head. Negative 2, but then that's 3 each, right? Oh, 12. Okay, so it's plus 6. Whew. Math is hard. Okay, so plus 6 going to a plus 3, that's going down, right? You got to go to the other thing and see, can we make, do your H's and O's last. They're always in the solution, so we're not dealing with those. Can we make that I go up then? Yeah, what does it go up to? I2. Okay, so with that being done, I can't get rid of that H. I can't just throw it out. So to balance this, I'm going to need to tack water on, right? Now here's where students are confused. The Na, the Na. Well, the Na, once that solid hits the liquid, what happens to it? It dissolves. So what's Na now doing? Ah, hi. I'm Na plus. I'm just watching. Okay, so that's what you do with the Na. You can't get rid of it. You can't get rid of it here because it said solid. You can't get rid of it here. All right, so you're going to go and balance all this stuff, and it's going to be an ugly one to balance. I'll probably never give you one like this on the test to balance. 2 there, 3 there, 2 there, and a 7 there. Okay? For this one, I'm just going to give you a note. Don't balance this particular problem because it's ugly, and I'm not going to mess with it. I don't even think I can get it to balance. I just want you to practice with the product prediction. Back in the day, you didn't have to balance these equations on the AP, and it was so much nicer. But now they're being mean. All right, potassium permanganate, it doesn't say, so we're going to assume a solution. What do we write? MnO4 minus is mixed with an alkaline. What does that mean? Nope. Basic. So what does it mean to be basic then? Hydroxide's added. Solution of sodium sulfite. What am I going to write? Nope. Solution, SO3 minus 2. I'm not even going to put the sodium in there. All right. I smell a rule. What does an alkaline solution of permanganate make? It's MnO2, isn't it? All right. So permanganate, manganese went from a 7 to a 4. So that went down. All right. So we have to make this go up. We're going to look at we have to look at the polyatomic. That's the only thing that left we can make go up. Now I'd say it would decompose to go to a gas, but here's another trick I want you got to pay attention. What is the oxidation state on that sulfur? +4. If I were to go to SO2 or SO, what did I do to the charge of that 4? Lower. But I can't, right? I got to go up. What's something I can do where I add oxygens and make it go up, and it's something you know? Yep, sulfate. Again, you never make anything you don't know. Don't ever freak because you know what you're making in all of these scenarios. Okay, next up. Let me take a little recording break right here. Pause. No, I'm going to do it. Okay, I'm going to change mine. This is going to be a very rare occurrence, but I'm going to show it to you because it's important for you to understand what's going on when you put a metal like this into an acid. So this is going to be, again, they didn't say it, but this is a solid. So if we have copper 2 sulfide solid, it says oxidized by dilute nitric acid. What do we write for nitric acid? It's a strong acid. So what do we write? H plus NO3 minus. Okay, we break it up. Now, here's the dealio. When you see something like this, the nitrate is actually reacting. This is the only time you put your nitrate in the equation. Any other nitrate we're not even going to put in there. Because it's reacting with some sort of coinage metal, we include it. So what gas comes off of that? Yeah, because this is -1. Yeah, NO2 would be fine. So that goes down in charge, right? So now I have to find something that can go up in charge. So this takes precedence. This is first step. Anytime you react nitric acid specifically with some sort of metal or metal ion, the nitrate is reacting. So because this actually will go down, we have to make something go up. Copper here is 2. Can it go up anymore? Nope. So what's all that's left? What does S-2 go to go up? Sulfur solid. Okay. So just like that sodium in the previous problem, the copper now is just hanging out going, hey, I'm still copper 2, and now I'm blue. I'm making a pretty blue solution, but I haven't changed oxidation state. Okay, and then what do we need to tack on to balance? Yeah, well, I put 4, but waters. And then don't worry about balancing on that, okay? I just really wanted you to kind of see the big picture. In case it does show up on the AP, I'm not testing you on this particular type of problem, but in case it does show up, I want you to at least have seen it. All right. What? Yeah, I'm recording. I'm at 33 minutes and 29 seconds. All right, a solution of potassium iodide. What do I write? I minus is added to an acidified solution of, you can't see it, people at home, but on your notes it says potassium dichromate, and it's a solution, so Cr2O7 -2. Okay, I'm going to turn the recorder off. Y'all tell me what to do. All right, so there's your answer. Once it's all balanced, 6I minus plus 14H plus Cr2O7 -2 gives you 2 chromium ions, 3 iodides, and 7, it's a beautiful 7 waters. All right, now we're going to move on. That was all of your redox. I mean, yeah, the stereotypical redox with crazy oxidation and reducing agents. We're going to fly through combustion and single replacement because they're easy and they're all redox as well. So combustion and single replacement are what I call modified redox. It's important for you to know if a reaction is going to have changes in charge. If you know that, it's going to be so much easier. So the rules, I'm going to be really I'm really not even going to worry too much about rules for combustion. I'll jot them down, but don't memorize these because you're going to get to use them. Hydrocarbons, this is what you learned from Chem 1. Hydrogen, jeez Louise. Hydrocarbons plus oxygen makes what? Hydrocarbons or alcohols. You already know this, guys. Okay, and then forget the rules. I'm just going to tell you something else because the rules are silly, and I'll tell you why. Basically, you can oxidize, you can combust anything. When you're combusting, let's say I have ammonia. Okay? All we combust is we're smacking that on to every element. So when we did the hydrocarbon thing, we had C2H4, whatever, plus O2. We lied and said, oh, it makes CO2 and H2O. Well, yeah, it does, but the reason it does is this O smacks onto that and then smacks onto that. So that's all combustion is. It smacks on. Now, what do you make here? There's going to be some options based on how much oxygen they tell you. If they say limited O2, you make NO and what? H2O. If they say excess O2, what do you think you make? An O2, exactly. All right, so that's what the limited and excess will tell you. But how do you know it's a combustion? It says burned in air, added to oxygen, all those different things. And all you do is smack those oxygens onto your different elements. We balance now. That's why we balance. Okay? So let's do some problems where we're actually balanced. Methane is burned in the presence of oxygen. What do we make? Come on, quick. We got to fly. We got 5 minutes. Come on, come on. CO2 and H2O. All right. And so now we have to balance this quickly. So I want to balance first my hydrogens. I always do oxygens last. My carbons are balanced, right? So I need 2 oxygens, right? Okay. Okay. Done. Lithium metal is burned in air, not hard. You just make the compound you make following your rules of nomenclature. And what is the compound? Li2O. And then to balance that, we need a 2 there and a 4 there. Okay, next up, zinc sulfide is heated in an excess of oxygen. Solid zinc sulfide heated in an excess of oxygen. Smack, smack, what are we going to make? Zinc oxide and excess oxygen. That's what tells us whether it's the O2 or the O on the back of the nonmetal. So that's SO2. And then to balance this, just to save time, I'm going to do it for you. All right. And the last one, a piece of solid bismuth is heated strongly in oxygen as a bird flies overhead and creates a beautiful beach-like. Anyway, follow your oxidation states. Add, stand, fell, huge cups cracked. What's the most common, high or low? Low. Bismuth can be what? Which is lower? 3. So what's the deal? Bi2O3. And to balance this, we have 2 Bi and 3O2. Now I got to hustle to single replacement. The only one that I'm super concerned with is your push-up single replacement. You guys can read these on your own. But what was the push-up problem? A metal plus water, an alkali metal. What does that make? Come on, guys. I made a big deal about this and told you had to do push-ups. Hydrogen gas and a base and a hydroxide. Okay, so that's one we have to watch for. Let's just jump in and do these problems real quick. A piece of aluminum, and we still follow the same rules we did before, is added to a solution of silver nitrate. Do I write down the silver nitrate? It's a solution, so I don't write nitrate unless it's nitric acid, right? So what do I write? Ag plus. Remembering that single replacement is modified redox. Can I make something go up and down? Al plus 3 and Ag. Okay? And then balancing this, we get 3 there and 3 there. Do you realize that when you did this problem before, you wrote it all out, split it up, and did all this stuff? You did it in one step here. Okay? Small chunks of sodium. This is the one I was concerned about. I'll write water as HOH for now, just for you to remember. And so we make, this is the push-up problem, and it is redox. We make H2 plus, and NaOH is a strong base though, so I have to write it broken up. Okay? And then this is a push-up problem as well, and to balance it, 2 and 2. Chlorine gas is bubbled into a solution of, what do I write? Gas. Cl2 is bubbled into a solution of, what do I not include? The sodium. I love this problem. Something has to go up, something has to go down. Not Br, Br2. Okay, and not only is that, it's super easy to balance too. Done. What are what? I didn't hear what you said. Oh, turnings are like, you take a little, say you have like a cheese, block of cheese, and you take your knife and you go like this and it makes like a curl that comes off of it. That's a turning. But it's not cheese. All right, magnesium turnings are added to a solution. What do I write? Plus Cl minus. Going to metals first, can I make this redox? Absolutely. I don't need stinking chloride. What do I make? Mg plus 2 plus Fe goes all the way down to 0. Okay, so I know we did a lot today. Now it's time for you to practice this. Everyone, and including at home, your homework comes from the back of your handouts. So everyone turn to the back of your handouts. And I'm going to sign off with you guys at home. Homework, ask a friend. Bye. Comes from the redox. Your homework is the redox, the single replacement, and combustion problems. Y'all see those? They're called mixed problems. The homework comes from the mixed problems. Tonight you have to do redox, single replacement, and combustion. Please read the instructions. There's a bazillion of these to practice. I expect you to do these, guys. This is one unit I'm like, you have to do your homework. Do not balance the redox. Don't waste the time. When you get to single replacement and combustion, I want you to balance those. Got it?